and welcome to another WJEC A level physics question. This time it's question 5 from January 2013's Unit 2, and it's a question about energy levels and lasers. So we've got a diagram, or a simplified diagram, of the energy levels in a 3-level laser system. And for part A, we've got to work out the wavelength of a photon associated with a transition between levels U and G, the ground state. So this is a standard calculation where we can use lambda is hc over E. Not in the data book, something that you need to learn, but it's in almost every lasers question. H is 6.63 times 10 to the minus 34. C is 3 times 10 to the 8. And technically it's delta E here, where delta E is the difference between the two levels that we're looking at. So here that is 2.26 times 10 to the minus 19 joules. If you put those numbers into a calculator, you will end up with 880 nanometers, which would put it in the infrared part of the spectrum, which is a common question that they will ask you. Next, we've got to explain in terms of electrons and photons what happens in the 3 possible processes listed below, in which photons are involved in transitions between levels U and G or G and U. And we're going to assume that those levels are suitably populated in each case. Well, absorption is where an electron in level G absorbs, I hate to use the same word as absorption, but it absorbs the energy of the photon, or absorbs the photon and its energy, and rises from G to U. So basically the photon disappears, the electron takes the energy of the photon, and the electron moves up from level G to U. Now, stimulated emission is a long sort of process that we've got to describe, but it's a fairly standard thing that we're looking for. So I like to start by saying an electron in level U is caused to drop to G by a passing photon. Now, a lot of people want to put things in about the electron absorbing photons or whatever, but no, that photon just passes by. And that photon has to have the right energy. And that energy here is going to be the 2.26 times 10 to the minus 19 joules. Can't be any old photon, it has to be exactly the right amount of energy. So the electron in U is caused to drop to G by a passing photon of energy 2.26 times 10 to the minus 19 joules. What happens then is that a second identical photon, and it's identical in every way, energy, wavelength, frequency, and quite importantly phase, and things like direction and polarity as well. So that second photon is emitted when the electron drops from U to G. So now we've got 2 photons out from 1 photon in. And that basically leads to the idea of light amplification. We've got more photons out than we've put in. Spontaneous emission is an electron dropping from U to G. But with no cause, no stimulus if you like. Nothing actually forces it to drop from U to G, it just sort of drops from U to G randomly. So that should say with no stimulus. For part C1, we've got to explain what's meant by pumping in a laser. Well, this is the idea where electrons are given energy to raise them to a higher energy level. And the point of this is to get population inversion, which we'll talk about in the next part of the question. Now, population inversion is where we have more electrons in the higher energy levels than in the lower energy levels, and population inversion is essential so that stimulated emission is more likely than absorption. So let's put that down. So population inversion is needed so that stimulated emission is more likely than absorption. Now in stimulated emission we gain a photon, in absorption we lose a photon, and the job of a laser is to increase the number of photons, identical photons that we get. So we need that stimulated emission to be happening more often than absorption to make sure that we have an increase in the number of photons. Thank you very much for listening. Please remember to like and subscribe, and feel free to leave any comments. Goodbye.